In this video, I want to talk about the Cauchy Riemann equations. Cauchy and Riemann were both famous mathematicians from the 1800s. Cauchy is someone whose name you're going to see over and over in a complex analysis course. And so we'll see there's many things that are named after Cauchy in this complex analysis course. Riemann is a name that you've probably already seen before. If you've obviously studied calculus, you've seen Riemann integrals and Riemann integration and Riemann sums and the Stilts's Riemann integrals, and there's many things named after Riemann. So there's also famously the Riemann hypothesis, which is a statement about complex functions. So maybe you've heard of the Riemann hypothesis. Anyways, so these are both very famous mathematicians. We'll certainly see a lot more of Cauchy as we go on. So a lot of what we're going to study is due to him. What I want to do is I want to describe the Cauchy Riemann equations. And before I actually tell you what those are and what they mean, I want to introduce this idea. So let's say that you have a function f, and I don't care if let's do it this way. So let's say that we have, let's just do this with an example. Let's say we have f of z is z squared. If you think of z as x plus iy, where z is some complex number, it has a real part and an imaginary part, then f of z is going to become a function of two variables. And if you square x plus iy, you end up with x squared minus y squared plus I times 2xy. Okay, and so here, what the Cauchy Riemann equations are going to do is they're going to, this is going to be kind of a good reason for us to talk about partial derivatives of our function, because we have a function with two variables in it. And whenever you have a multivariable function, you can't talk about just the normal derivative anymore. You have to talk about partial derivatives if you're going to differentiate with respect to x or y. I mean, there's other things that you could do, like talk about the Laplacian or other stuff from Calc 3. But there's good reasons for us to talk about the partial derivatives. So let's start by thinking about the partial derivative of f with respect to x at the point z naught. And this is going to be the limit. So this is going to be defined as the limit as z approaches z naught of f of, let's see, if we're differentiating with respect to x, we're going to treat y as constant. So this will be x plus iy naught minus f of x naught plus iy naught all over z minus z naught. But here I'm thinking of, so here I'm thinking of z as being x plus iy naught and z naught as x naught plus iy naught. So z minus z naught is just going to be x minus x naught. And in fact, we can replace the denominator with x approaches x naught. Because if z approaches z naught, well, these are the same. So that really means that x approaches x naught, right? There's a correspondence there. So this is the partial of f with respect to x evaluated at z naught. And likewise, if we look at the partial of f with respect to y, here we're going to think of z as being x naught plus iy, because we're differentiating with respect to y, so we're treating x's as constants. And therefore z naught is going to be x naught plus iy naught. So then the partial of f with respect to y evaluated at z naught is going to be the limit as y approaches y naught, f of x naught plus iy minus f of z naught all over z minus z naught, which in this case simplifies to y minus y naught. Okay, and so these are the two partial derivatives of f with respect to x and with respect to y. Okay, so that's what we mean when we do partial derivatives. Is so just to say it again, we've talked about just the derivative of a function in a complex sense, and what's different there is that we're talking about the limit as z approaches z naught. But if we're talking about functions of complex numbers, then you have to think about all the possible paths to that complex number instead of just the two paths from the left or right that you would in Calc 1. So here we have to be a little bit more careful, but we can also talk about the partial derivatives. And so that's what we just defined there. It's the partial of f with respect to x and the partial of f with respect to y. And it turns out that there's a relationship between these two quantities, and the relationship is exactly the Cauchy Riemann equations. So we can call this a theorem, or we can just call them the Cauchy Riemann equations. And what this does is this tells us that, again, that there's a relationship between these two partial derivatives. So let's let f be a function from a set g to c. where G is open. Suppose f is differentiable at z0. So suppose f prime of z0 exists. And if that's the case, then the partial of f with respect to x at z0 is equal to 1 over I times the partial of f with respect to y of z0. And these are the Cauchy Riemann equations. I know that this is only one equation, but there's a way to view this as two equations, which I'll talk about. So going back just for a second to this function z squared, notice that what we did is we took f of z equals z squared and thought about it as a function of x and y, and then you end up with the real part and the imaginary part. So you have x squared minus y squared and 2xy. So let's think about what happens in that case. So if you were to have f of xy equals u of xy plus iv of xy, then let's think about what would be the partial of f with respect to x. Well, the partial of f with respect to x would be the partial of u with respect to x, evaluated at that point, plus I times the partial of v with respect to x at that point. And likewise, we could do the same for the partial of f with respect to y. That's going to be the partial of u with respect to y, plus I times the partial of v with respect to y. And so in particular, if we know that f prime of z0 exists, and therefore the two partials satisfy this equation, what that tells us is that the partial of f with respect to x, which I'm going to write as u sub x. Okay, let's just call it u sub x, just for simplicity. It's u sub x of z0, but just call it u sub x, plus I times v sub x is going to be equal to 1 over I times the partial of f with respect to y, which is going to be u sub y plus I v sub y. And if we distribute this, if we distribute the 1 over I through, what we're going to get is we're going to get u sub x plus I v sub x is going to be equal to, let's see, negative 1 over I is negative I. So it's going to be minus I u sub y. And 1 over I times I is just 1. So plus v sub y. And so what this tells you is that u sub x is going to be equal to v sub y, and u sub y is going to be equal to minus v sub x. So these two equations are really why we call them the Cauchy Riemann equations, is that there's two of them here when we think about it like this. Okay, and so let's think about this in terms of an example, and then in the next video we'll go over a proof of this fact. So let's think about an example. Let's just go back to f of z equals z squared. Z is x plus iy. And then we know that if we think of z as x plus iy, this shakes out to x squared minus y squared plus I times 2xy. Now we know that f is an entire function. Remember what that means is that it's differentiable over all values in C, and therefore it's holomorphic for all values in C. And if it's holomorphic for all values in C, those are called entire functions. So this one is differentiable everywhere. And so we can kind of make sense of this for any input that we want. So we can talk about this in general. But our u of xy is going to be x squared minus y squared. That's the real part of the function. And then the imaginary part of the function is going to be 2xy. And then what I want to do is I want to look at what's the partial of u with respect to x, partial of v with respect to y, partial of v with respect to x, partial of v with respect to y. And then I want to make sure that they actually satisfy this equation. And of course they will. But the partial, I know, spoiler alert, but the partial of v with respect to x is 2x. Partial of v with respect to y is minus 2y. The partial of v with respect to x, so we're treating the y's as constants, so we get 2y. And then the partial of v with respect to y, we're going to get 2x. And indeed, we get that u sub x is equal to v sub y, and u sub y is equal to minus v sub x. Okay, so this function is differentiable at every point, and therefore the Cauchy Riemann equations are going to be valid at every point. Okay, so again, in the next video, we'll talk about a proof for the Cauchy Riemann equations.